Hello, ladies and gentlemen. Thank you for being here today. My name is Emna Amri, and I'm going to present you my PhD project involving remote sensing, machine learning, and operational applications. I want particularly to thank the member of jury for accepting to review my work. This project is financed and initiated by Total Energy Company in collaboration with the LISTIC laboratory of the University of Savoie-Mont Blanc. Here is the list of my supervisors. Several people are involved in this project. I'm going to have an extended list by the end of this presentation. First, I'm going to present you the background of this project. Then I'm going to present the conducted works. Let's start. What is offshore oil slicks? Oil slicks are some patches that appear on the sea surface. They can originate of two types. The first type is called sips. It's natural oil that appear on the sea surface. The second type is spills. Oil spills are made by human beings. They are anthropogenic oil. They involve health, safety, and environment aspects. The both category of oil slicks, they are searched by several communities such as environmentalists, local authority, and particularly the industry, which is our context. So let's see how oil slicks are detected by the related works. On the state of the art, there are two different sensors. There are what we call passive sensors and active sensors. For the passive sensors, as they are called passive, they are dependent on the sunlight. They can operate only where there is sunlight. However, the active sensors, they have their own energy. Here is two examples of oils. The first one on the left presents the natural oil, what we call sips. Here is a zoom in on some colorful films on the sea surface. This second picture presents an anthropogenic spills. We can see that there is a ship and there is some discharge of oil. The second category is the active sensors. On active sensors, we can have acquisitions 24 hours a day, 7 days a week. So we are not dependent on the sunlight, and we can see the oil slicks as dark patches. We can see that the image are gray level, and the oil slicks, they appear as dark patches. Why they appear as dark patches? Here is the sea surface, and here are some oil patches highlighted in black. We can see that oil slicks, they dampen the sea surface, and they make the surface more soft. Here is a radar. For example, it's a Sentinel-1 radar. It's going to send its own energy on the sea surface. This energy, what we call electromagnetic waves, it's going to be back-propagated to the sensor. We can see that the oil slick impact the signal. So that's how we can see oil slicks on the sea surface, and that's how it appears dark. This category of sensor, it's the most interesting in the case of oil slick detection, as it can provide continuously acquisition and it has its own energy. Let's see a real SAR image. This is an image of Sentinel-1. It has 10,000 by 10,000 pixels. We can see several phenomena on the image. The patches highlighted in blue and red are oil slicks. The one highlighted in blue are the natural one. The one highlighted in red are the anthropogenic one. We can see that there is other phenomena on the sea surface. They are similar to the oil slick. They can appear as dark or as white patches. So the task of detection actually is realized by what we call photo interpreters. They are expert human beings doing some zoom in, zoom out on the SAR images in order to find these small patches that we call oil slicks. In order to find them, they sometimes need to have other contextual information, such as the wind information or the position of infrastructure. So the analysis of an example of this image, it takes from 10 to 20 minutes, which is a time consuming, and it cannot keep up with the amount of the acquisition nowadays. Imagining if you want to analyze all the sea surface, analyzing images of this size, large and complex images with adding some information, this cannot be handled by photo interpreters. That's why we need to assist them. We need to support these photo interpreters And this is my project of PhD. In this project, the objective is to automatically detect the oil slicks of two types, the natural and the anthropogenic, while being robust to some lookalikes, some phenomena that look dark, exactly as our target, but they are not. This category of phenomena, it's called lookalike, which is a big challenge in the research. Based on the literature and on the state of the art, the main challenges of this area is the high variability of our target. As we saw, we have two categories of oil slicks, natural or anthropogenic, in any place in the world. So it has a huge variability of size, type, and shape. Oil slicks, they are covering small amount of sea surface compared to the huge amount of sea surface. There is a contextual variability. For example, a slicks appearing on the south of Africa, won't have the same characteristic as a slicks appearing in another place. And we have the biggest challenge, which is the similarity of our target with other phenomena. Doing the literature of this domain, the first category of detection is what we already saw, the manual inspection, which cannot keep up with the amount of acquisitions, and it's also costly as it involves human being analysis. The second category of approach, what we call convolutional approach, it consists of classical feature extraction, dark spot detection, and classifications. This category, it is efficient, but only for one type of oil, either natural or anthropogenic. So there is a lack of fully automatic on both types, and there is a problem with the lookalikes. There is a huge amount of lookalikes appearing as a slick. This category also focus only on one modality. They are using only the SAR data during the learning or the process. The third category in which we are interested is the end-to-end learning approaches, including the machine learning and deep learning approaches. This category, it's a promising category, giving promising results in several domains, and there is several architecture and way to explore it. But in our context, there is only few words. And when we say deep learning, AI, we say always we don't understand the results. It's a black box. So it lacks of result explanation. This PhD is going to contribute on several aspects. The first one is we are going to try to automate, to make the task of detection fully automatic. We are trying to detect both types of slicks, which have been never done in the literature before. We are going to try to fuse all the relevant data for this task, and we are going to give explanation, visual explanation to our results. Here are the three main contributions. The first one is based on the definition of our problem, task, domain, and metrics. The second one is the proposition of our deep learning models. And the third one is giving a clear explanation on the results. Let's start with the first one. Among the AI approaches, which approach we need to use? As we have annotations realized for 10 years or more with human beings, we tend to use what we call supervised learning in order to assist the photo interpreters to do this segmentation, this kind of drawing the polygons of the slicks. On the literature, we have three approaches. The first one is object detection, where we highlight our target with a bounding box. This approach is not that relevant in our cases. For example, imagining we have a big slick, a big thin slick that is diagonal, we will have a huge bounding box that is covering a huge sea surface. So the remaining category, we have two. The semantic segmentation, where we can identify our slicks from the backgrounds, and the instance segmentation, which do the same task of the semantic segmentation and also identify the instances. We can see here we have three slicks instances that are separated, and here we have all of them on the same color. I'm going now to present what are the available data to use. We have SAR data, the annotation of the expert, and the wind speed. Let's start with our main data, which is synthetic aperture data. It's a category of SAR data with better resolution. Here, we use two categories of sensor with different characteristics. We can see here the difference of the pixel size and the resolution. We cover several areas on the sea surface. We can see here both InVSAT and Sentinel-1 areas. And we use large-scale and real monitoring scenarios. All the data that we are using, they are real data used by photo interpreters. For all this SAR data, we have the associated annotation, what we call the ground truth. We have several annotations realized by a variety of photo interpreters. This variety involves some variety also in the way of annotation. As we can see here, for example, it's a global annotation where we have some clean sea area. We can see also here that the annotation is very precise. It's including even the small patches around the slicks. In the pipeline processing of this annotation, we have some issues. Here are the main ones. We have some potential alignment issues. We can see here, for example, a shifting of the polygon of a few pixels. And we have during the rasterization process, which is moving, rasterization means moving from the polygons to a matricial format. We have some issue when converting these polygons to rasterization. We have more instances. For example, for one annotation, it can be converted into three instances instead of one. So all these issues need to be taken into consideration in the processing. So the uncertainty of the annotation should be considering in all the process, the training and also the validation. Let's go to the third main data, which is wind speed. As we saw that the oil slick dampen the sea surface. So the clean sea, it's always rough due to the wind speed. So the wind speed, it's a valuable information to the detection process. So we choose to use wind speed estimation based on empirical geographical model functions called CH-Mod 5. It's based on the SAR data, particularly the VV channel, as it's very relevant channel for the oil slick detection, even with conventional approaches. We can see on the left an image of the Sentinel-1 sensor, and we can see on the right an image of the wind speed upsampled to the SAR sensor, as the wind speed information is have less resolution than the SAR sensor. We can see here that all the dark patches, which are oil, they appear a little bit less on the wind speed, and we can see that the black area present low wind speeds. Now we have the SAR data, the annotation, and the wind speed. Let's build our workflow. Here is the data workflow. The bounding boxes presented in orange are the processing realized within the total energy company. The green one are the contribution of this PhD. Let's start with our raw SAR data that we acquire from the ESA agency. There is a first processing of the SAR data where we do some calibration, some land covering in order to have visible, clear images. From that images, we estimate the wind speed, relying on the VV channel. Then we have, as we saw, we have some underestimation on the sea surface that we need to process for later validation process. Here, there is the main step, which is the alignment of the annotation, the SAR data, and the wind speed. After the alignment step, we need to split our data in order to use a machine learning approach. We choose to use small crops for the training, as deep learning cannot have as an entry big images, and we leave some test images with a high size. We are going to see the statistic of the training and validation sets. Here an example of a slick and an example of a sea and lookalike. Within the creation of the data set, we add some lookalike. With experiments, we generate some lookalikes in order to make the database more representative. We use more than 3,000 crops in the training. We can see here that we have a huge imbalance between our target and the background, which is the sea and the lookalike. Let's move to the test set. During the test set, we choose to use big test images. Why? Because the purpose is to help the photo interpreters. The photo interpreters, they use real images, like this one, not crops. So we have several layer images with more than 200 annotation of both types, the spills and the slicks. We can see that also in the data set, we always have this imbalance between our target and the background. We choose the category of approach we are going to use. We present the data, how we are going to evaluate the results. Based on the state of the art and on the segmentation approaches, we have two categories. We choose two categories. The first one is pixel level classification metrics. They are standard metrics such as IOU, precision, and recall. But as we have saw the imprecision of the annotation, we cannot expect to have a high IOU in our results. And operational needs and exchange of, with photo interpreters, the real needs of the company is to have a level evaluation. How many good instances, how many instances we miss, and if there is false alarms. So this category, it's more appropriate in our cases. I'm going to present now the baseline, the first baseline. We choose to use AI approaches. Why? I'm going to prove why. Because deep learning approach, in our case, it's more suitable. First of all, because it manages high problem variabilities, which is our case. It has flexibility and adaptability in several domains, and it enables us to simplify our complex problem with a deep of cascade of nonlinear functions. Among all the deep learning approach, we are going to choose two. The first one is the instance segmentation, what we call mask RCNN, and the second approach chosen is semantic segmentation, which is FCDenseNet. I'm going to present these two approaches. The first approach, what we call mask region-based convolutional networks. This approach is multi-stage and multitask approach. Starting from the input image, we have a step of feature extraction. We extract the feature of the input. Then we have a step of regional proposed network, where we propose a region where there is a potential of having the target, of having oil slicks. After that, there is a step of alignment to adjust these bounding boxes. And then we have our three heads, our three tasks. The first one is identifying the class of the target. The second one is detecting it. And the third one is the segmentation mask. This approach is very complex. It needs to be, we cannot train it from scratch. We need to do transfer learning. This transfer learning is good, but it can include some bias linked to the transfer of weight from, for example, multimedia domain to SAR domain. As it's a complex architecture, it requires high number of parameters and consequently high computer resources. Let's come to the second approach. The second approach is an approach autoencoder, which is similar to the famous UNet architecture. However, this approach is characterized by the dense blocks. We can see here several layers with several skip connections. Starting from the input, we have an encoder section where we try to reduce the dimensional of the data to a high abstractual level. From that, we go to the output where we have our semantic segmentation mask. We can move from this semantic segmentation mask to the instance segmentation mask by applying some post-processing of composite component. This architecture is simpler. It's monotask model, and it doesn't require pre-training. We can customize it. We can train it directly on our data without having any bias. However, it have also high number of parameters and require computing resources. We focus on this approach and we optimize it regarding the needs of the company, where we apply some normalization. We remove the batch norm. We apply some normalization to optimize the convergence of the model and to optimize also the parameter numbers with a reduction of the skip connections. So we reduce the number of parameters from 9 to 8 millions, the inference speed minus 30 seconds, and the convergence time while training 2 hours minus. I'm going to present the comparison of these two approaches. Let's start with the standard matrix. Here we have on the top, we have FCDenseNet results. On the bottom, we have MassCRCNN. If we see the detection rate of both, we can see clearly that FCDenseNet detects much more than MassCRCNN. Both approaches, they have false alarms, and FCDenseNet have better IOU of SLIC. If we want to analyze these plots, let's see the x-axis, which represents the speed of the wind going from 2 to 6 meters per second, which is the range where the photointerpreters can see the SLICs. And here we have the instance number of the SLICs. So if we want to analyze the detection rate of both approaches within the 2-3 meters per second, we can see that we have almost 100 detection by FCDenseNet, which is the green color, and we have around 10 misdetection. The same thing with MassCRCNN, but with higher number of misdetection. If we want to analyze the false alarm rate, we need to look at the y-axis on the left, on the right. Here we can see, for example, on the low wind speed area, we have high number of false alarms. Same thing with the mediums, with the wind speed of 2-3 meters per second, we have some false alarms. And we can see that globally, both approaches have almost the same results. This analysis also is done regarding the SLIC of the size of the SLIC. We can see here the size of the SLIC from 20 hectometers square to more than 1,000 hectometers square. We can see on the y-axis the instance number. We can see, for example, that the SLICs that have medium size between 20 and 500 hectometers square, they are almost all detected. There are a few missing instances from FCDenseNet and much more with MassCRCNN. And we can see that we have several false alarms with big and medium size SLIC. Let's see real results. Here we have a SAR image with several SLICs that are highlighted in green by photointerpreters. I'm going to show you the results of FCDenseNet and MassCRCNN. We can see here the prediction of FCDenseNet highlighted in red and the prediction of MassCRCNN highlighted in yellow. We can clearly see the reflection of the IOU values. We can see that the red color is covering more the annotation. If we do some zoom in, we can see that almost all the annotation are detected partially or fully by both approaches. We can see here, for example, we have the instance all covered by red, and there is some patches on yellow. We can see also that there is some over detection. There is some detection that are not supposed to be SLIC. These false alarms, they are of two categories. The first category, it's a small oil slicks that are surrounding an annotation. Here is an example of the ground truth in green and some false alarms in red outside. These false alarms, based on the photointerpreters, they are some oil slicks that are not annotated because they are too small to be annotated. The second category is the real false alarms category, which is the lookalike, where we find some area of low wind or algae or upwelling, and this, we need to reduce this. This is the main challenge. We need to reduce this. So, a preliminary conclusion for the baseline comparison. We find that FCDenseNet is more flexible and more suitable for our case because it's trained directly on the data. We don't have a bias of transfer learning. But we find that we have high false alarms. So let's go further. How can we reduce these false alarms? Can the wind speed information help us as it's helping the photointerpreters in their process? Here we come to the main contribution of this PhD, which is the proposition of deep learning model based on multimodals. Based on the state of the art, there is several ways of fusion, of using different data. We have early fusion, a category called early fusion, and we have a second category called late fusion. The early fusion category presents the direct fusion of raw data or pre-processed data. Here we have the fusion step, and here we have the model, the deep learning model, and we obtain the prediction. So this is direct raw fusion. The second category of fusion is more flexible fusion, where we can have a specific model pre-processing for each modality, and then we fuse them within the model and we obtain predictions. So here we are going to use multi-modality models. We have the two modalities, the SAR and the WIN. Let's see this category on our cases. We are going to focus on our improved FC-DenseNet, and we are going to use to propose you the new architecture called Fuse FC-DenseNet. This architecture is based on the improved FC-DenseNet. Here we have the encoder section, and here we have the decoder section. We add the new modality, the wind speed modality, beside the SAR modality. We have two numbers here, the 1 and the 2. The 1 refers to the early fusion way. The 2 refer to the late fusion way. I'm going to go through details on that in the next slide. We are going to compare all the fusion model with the baseline with our SAR one modality model. The first fusion is the Earth fusion. We can see here that the wind speed modality, it's inserted, it's fused directly with the SAR modality. So we have a new modality on the input of the model. Regarding the late fusion experiments, we did several experiments. I'm going only to present the most relevant one. The first one, that we call here T1, present the insertion of the wind speed, the fusion of the wind speed after an operation of pooling, where we reduce its resolution to the real resolution, and we insert it in the second block of the encoder section. The T2 experiments do almost the same thing, but we add a dense block before the fusion of the wind speed, and we still in the second block. The third fusion, we do some pooling, dense blocks, and we go later on the model to insert the modality in the third blocks. Here we can see clearly that here we have more flexibility to add some pre-processing, to change the level of insertion. And we have also, the more deeper we go, the more the complexity and the scale of the pre-processing is high. Let's see the results. I'm going to compare all the fusion results with our baseline, the only SAR. Here we have the pixel level metrics and the instance level metrics. We can see clearly that we keep the same good detection, and we reduce the false alarms of around 300. But we can see also that with the early fusion, we have some degradation into the pixel level metrics. Here is the results of the late fusion. The late fusion have almost better results for good detection. We can see here that we have 200 good detection among 214, and we have reduced the false alarms from 1,600 to 1,000 almost. We can see also that we have also a good IOU rate. We have 0.3 of the SLIC IOU. There is several compromise between the pixel level and the instance level. The choice of the good experiment between the late experiment fusion is always the decision of the photo interpreters, whether they want to have high good detection with less false alarms, or they want to have medium good detection with less false alarms. A preliminary conclusion. Here we compare the monomodal models with the fusion models. We propose a new architecture called FuseNet that report better results, that reduce the false alarms, that are the challenge of the state of the art. We also confirm the importance of the wind speed not only in the validation step, but also in the training step. We also show that the late fusion is more appropriate in our case, giving some compromise between the false alarms and the good detection. Now we have results. We propose an architecture. Let's go to deeper metrics evaluation. And here comes our third contribution, which is explaining our results. On the field of deep learning and machine learning, there is a category that we call explainable artificial intelligence. Why this category is very important? Because with deep learning, we have complex architecture. We have results that we need to trust and to understand how the decision is made. And in our context particularly, we need to explain to the operational, we need to explain to the operational the results and to give them interaction with experts. So how can we do that? In the AI explainable method, there is a category that we call visual explanation, where we give a visual explanation of our results. We pick two techniques. The first one, call it SHAP, and the second one, call it RISE. I'm going to start explaining the Shapley additive method. This is an approximation of a complex deep learning model, a black box deep learning model. We want to approximate it with an understandable explanatory model by a linear fusion combination. Here, the goal is to find the collusion between several features that we can call simplified features, simplified input, while satisfying three properties: the accuracy, the consistency, and the missingness. So this technique is going to help us to know the importance of each feature, and this technique is only existing actually for data such as tabular data classification. It's not adapted to our context. That's why we need to adapt it in our context. This work is realized within an internship in this PhD. Here is the adaptation of the SHAP explanation technique. As an input, we have our SAR image, and we have a grid of hexagonal shapes, what we call it our superpixels and our features with the vocabulary of SHAP. We generate several masked symbols where we can find there is several superpixel hidden. We give this as an input to our deep learning black box model to obtain some predictions. The predictions here are presented in probability maps. In this step, we need to choose what is the pixel that we want to understand and what is the class that we are interested in. Giving these two information to our Shapley explanation computation, we get as an input this explanation. We can see here our input is covered with a grid of colors. We have two range of colors, the red and the green. The red color are referring to the negative contribution, which means this area are inhibiting the decision. And the green area, they are giving an excitement to the decision. For example, if we want to analyze this pixel, we can see that the clean C area, it's contributing negatively to the decision of this pixel as a slick. So overall, this technique is giving us both contribution, the positive and the negative. We are moving to explain the second technique, which is almost the same thing, but using another way of hiding and masking the data. We can see here that we have masks of several shapes. We give our samples to the deep learning model to obtain our heat map, where we can see that the high contribution are with red color and the low contribution are with blue color. This technique shows only the contribution. We cannot know if it's contributing positively or negatively to the decision. Let's present the results. We study this explanation based on several factors. Here we are going to study the field of view behavior of the model. Our input data present the SAR data with the several superpixels. We have the annotation of expert highlighted in green, and we choose two pixels. The first pixel presents a pixel of slick, but we can see it's not fully black, it's slick and C. And the second pixel, it's a clean C area. We are going to compare the monomodal approach with the multimodal approach, using SAR data and using SAR and WIN data. The first pixel, which is classified as a slick, and it is a pixel of slick. Here is the output. We can see, for example, that this area is contributing positively to the decision of this pixel. So we can see clearly that the black areas, they are contributing positively to the decision of the slick. However, the clean areas, they are contributing negatively. We can see the second example, which is a clean C pixel, where we can see that the clean C is contributing negatively and the black C is the black area is contributing positively. If we compare both monomodal and multimodal approach, we can see that here the intensity are a little bit lower than here. We can see that the intensity of colors with the fusion models are higher than the intensity of colors with the monomodal models. So the field of view of the models, based on the decision, it can have a large field of view while deciding, as it can have a tight field of view in the case of the pixels. Here we are going to study the sensitivity of the boundaries. We can see an example of a slick which is thin and large. We pick two pixels, one on the border in the side of the clean C and one inside the slick. We can see that the first pixel, which is on the border, is a slick pixel. We can see that the network, the model, is based its detection on the boundary. We can see that we have a shape of a slick in a green color, and we can see that the clean area, it's highlighted as red. The same thing, it's clearer here with the second pixel. It's a slick pixel, and it's inside the annotation. We can see that all the area within the slick and on the border is highlighted in green. So we can see globally the importance of the slick edge in the decision of the model for both cases, the slick and the C. Here is a comparison between SHAP and RISE of the same two pixels. We can see here the SHAP results that I already present and the RISE results. We can see that there is a similarity. We can see that there is a similarity in the highlighted area. Here the contributions are in this area, and the same thing with the RISE. But we can clearly see that with SHAP we have more information. We have the type of the contribution, whether it is positive or negative. However, with RISE we can only know the area contributing. A conclusion regarding this explanation part. Regarding the decision on the slick, we have a nearby slick impact on the decision. We have more confidence intensity with the multimodal models that we propose. We analyze these results based on two types of pixels. Three clean C pixels where the field of view is large. In the case of the slick pixel, the field of view is a little bit limited. And we saw that the age of the slick is very important in the decision of the model. I'm going to finalize with the conclusion and perspectives. In this PhD, we achieve the assistance of oil slick detection. We give a tool to the photo interpreters to assist them into their detection. We compare two monomodal deep learning models, which we show that deep learning approach, they give good results, but they have several false alarms. That's why we go further to propose a multimodal approach where we fuse the SAR modality with the WIN modality, and we reduce the false alarms. We establish a deeper analysis on the results, including some contextual factors that are used also by photo interpreters. We conclude that there is a feasibility into the focus on the two categories of slick at the same time, which is not the case in the literature. We are able to detect both natural and anthropogenic slick with the same model. We use large-scale real monitoring and multi-area on this study, and we fuse several data. We fuse several data with several nature to improve the detection. We also have a lot of exchange with the photo interpreters, and we can say that even we have automatic tools, the AI approach, they require the photo interpreter's expertise. Regarding the perspective, we have short-term perspective. We need to incorporate the results into the workflow energy, the total energy company workflow. We can study the uncertainty of the model. We already start doing that playing with the dropout of the model and finding that the model is not certain on the age of a SLIC, we can go further on this way. There is also another interesting area, which is introducing another modality, such as the infrastructure position modality that we already use, and there is some results on the third chapter of the report. The long-term perspective include the feasibility of including the explanation into a reaction with the photo interpreters. So an interface that the photo interpreters can explain and see the results of explanation. We need to ensure the active and continuous learning of our model. You know, deep learning with several acquisition and continuous acquisition, we need to keep on with all the annotation and all the acquired data. We can also study particularly the SIP detection with time series. During this PhD, I contribute to several publications. Here is the main ones. As I told you, within this project, there is several people who contribute. From the side of the Total Energy Company and from the side of the LISTIC laboratory. I want to thank all of them, those who contribute with helping, financing, and supervising. And thank you for your attention.